Alrighty, so we're updating our table of contents, putting in page 38 for exponential models. And we used our scissors already today because we were cutting out our foldable, but we will kind of hold off on gluing it down just yet because we got to make sure we place everything because we are going to write some stuff down by hand to start. Okay, so go ahead and turn over to page 38 in your books, and go ahead and title it Exponential Models, and make sure you get down to the goal. We are going to be using our conclusions from our investigation to apply like the concepts that we realized from the investigation to our application problems. So to start off with today, we're going to actually look at our investigations. Go ahead and pull out your investigation first. We'll go over that just to make sure that kind of we're on the same page, and then we're going to use these different conclusions that we can draw from our investigation to apply them into our application problems. Now, this investigation, it was shorter than the other one, and after doing the first one, we kind of should have been used to like what you all should have done, right? I gave you a few graphs, you had to plug them in, and then you kind of had to draw conclusions based off of it, right? So I want to hear from everybody today. And unfortunately, it's a small class. I want to hear from everyone, literally, in response to some of these questions, okay? So you had to graph these few on the same axis. 2 to the x, 3 to the x, 10 to the x, and then 1.3 to the x. And every single one of them was a part of this type of family, where it was y equals a to the x. A being the base, the number. So, for a is greater than 1, what effect does changing a have on the shape of the graph? Like when you graph these, how did changing a change your graph? Yes?
As it crossed over the y-axis, it became more vertical, and the further away it moved from 1, like the bigger it got, the more vertical it became.
The more vertical it became? Okay. So the bigger the number got, the more vertical it became after the y-axis. Anybody want to add on to that? Maybe they say something different? Yeah?
The domain.
What about it?
It got bigger or smaller.
It got bigger or smaller? Okay.
Like it changed.
It changed. Changed how? What was the domain for 2 to the x?
It was 0 to 2.
Let's see. All right, and make sure too you guys have your calculators too, so you can. All right.
Oh, not 0. My calculator was like this.
Oh.
Negative infinity.
To what? What do you think is happening after beyond positive 10?
Gonna reach an asymptote, right? You go to 0.
After, like that, going that way.
So it just goes infinity?
Mm-hmm. Like if I were to trace it, right? If I just click regular trace and I just go over using my over arrow button, what's happening to my x's?
It's getting bigger.
And what's happening to my y's?
Bigger too.
They're getting bigger too. And it's just going to keep on. So what do you think?
Positive infinity.
To positive infinity. So our domain is actually negative infinity to positive infinity. Okay? So not quite our domain changes. Anyone else? Well, give me one more person. One more person. Tell me what they said. Yes.
The bigger the A, the tighter and quicker the y coordinate increases.
Tighter and quicker, the y coordinates increase. Okay. So basically, we just graphed 2 to the x. Let's plug in a 3 to the x. Actually, let's plug in 10 to the x. That's going to make the big difference. And then let's plug in 1 point, was it 1, 2, or 3 to the x. And let's see how they change as well. So there's 2 to the x. The red one is going to be 10 to the x. Oh, that's like really steep, yeah. And then here comes 1.3 to the x. And now it's a little bit wider, yeah. So it looks like as a changes, right, the bigger that a gets, the steeper it is. And then, of course, vice versa.
What is steeper? The line?
Yeah, like the curve. Because as we saw, we had 2 to the x going like this, but then 10 to the x was like this. And then, of course, 1.3 to the x was a little bit steeper. So it's not as big as 2 to the x, but it's still, greater than 1, but it's just a little bit wider. Okay? Do you guys see that? Yeah? Okay? Let's look at number 2. Then I had you graph these other few. 2 to the x, then 2 to the x plus 1, 2 to the x minus 2. They were all a part of this particular family. Okay? Where c was some constant. What effect did changing c have on the position of the graph? Remember somebody different.
The y-intercept changed.
The y-intercept changed?
Yes. It changed the range.
It changed. Okay, so I hear change the range, change the y-intercept. So position-wise, what happened position-wise? Like you had regular 2 to the x, then you had 2 to the x plus 1, and then you had 2 to the x minus 2. What happened from the original 2 to the x?
It went higher.
It went higher? Both times?
No, the other one went lower because it was negative 2.
Because it was negative. So it looks like the changing of c changes if it goes up or if it goes down, right?
Mm-hmm.
Did changing c have any effect on the shape?
It like gave it a more rounded shape.
What do you mean more rounded shape?
Like, how do you explain it? It wasn't as steep. Like depending on how big it was,
Uh-huh.
it like made it go out farther.
Okay.
It made it wider. Yeah, wider.
All right. So made it wider. Let's see.
The x minus 1 was the widest, and then 2x was the least.
I thought it made it
Wait,
longer.
plus 1 was the
Let's take a look. The blue is the 2 to the x. Let's take a look. Here comes the plus 1. So you're right. It definitely changes. It's a y-intercept. And then here comes the minus 2 one. Are you sure the shape changes?
It just seems like they
Just
start
the
to
way-
curve
they
either
just
sooner
start
or
in
later.
different places.
But just because, well,
Or they'll start like they hit the y.
they hit the y at the different places, but let's say, like, if I were to move this graph back up, so the black one back up so that it lied on top of the blue one, is it still going to be the same shape?
Yeah.
And if I move the red down to match it with the blue, isn't it still the same shape?
Yeah,
Yeah,
it
yeah.
just looks different the way it is together.
Mm-hmm. It does look a tad bit different, but it doesn't have no effect on the shape of it. It still looks in the same fashion. Still looks in that same fashion. What's the horizontal asymptote of each graph? Ollie, what was the horizontal asymptote of 2 to the x? I have it up here still, the blue one. What's that horizontal asymptote? The blue one. Remember, horizontal asymptote is a line that's getting really, really close to but never crossing or touching. It's going down. 5. Horizontal asymptote, yes.
Oh, I was confused. Like, what is an asymptote?
And-
No.
An asymptote, whether it's vertical or horizontal, is basically a line that the graph is going to get really, really close to but not cross or touch. Okay, we dealt with vertical, well, you would have dealt with vertical asymptotes, back in other classes when you were dealing with, like, rational functions and things like that. In this particular case, these exponential functions, they don't have a vertical asymptote because their domain is negative infinity to infinity. But they do have a horizontal asymptote. If you notice, every single one of these is flattening out, which means it's not going to be lower than a particular value. And if you're ever unsure, especially with this type of investigation, you could have traced it. Like right now I'm on 2 to the x. If I go to the left, because that looks like where it's flattening out, what's happening to my y values?
I would think it was 0.
They're getting smaller and getting closer to what number?
0.
Do you ever think it actually will be 0?
No.
No.
And I can keep following this all the way out, and it's going to keep getting smaller and smaller. What does that mean? The e to the negative 4.
It's just really, really
It's really, really small. So for the blue one, the horizontal asymptote is
Y
y
equals 0.
equals 0, and it is an equation. Y equals 0. But exponentials don't have vertical ones. Let's look at the red one. I'm going to change lines. This one's getting really, really close to what number?
1.
So my horizontal asymptote is y equals. And then from the last one, Do I need to go to it, or you guys think you know what it is?
-2.
It is -2. So for this one, it was -2. For this one, it was y equals 1. So in general, what's the horizontal asymptote of 2 to the x plus c?
Whatever C is.
Whatever c is. And that will always be the case. It doesn't matter, but whatever number's being added at the end, or it could even be at the beginning. Whatever's being added to that exponential part, the part that has the exponent in the base, it's going to be y equals c. Okay? Questions? How are we doing so far in this investigation? Better than the first time? Okay. Then I had you graph these. 2 to the x, 2 to the negative x, 5 to the x, 5 to the negative x, so on and so forth. What was the y-intercept of each graph?
1, 0.
Wait, 1, 0?
Right? 0, 1. Sorry.
0, 1. Uh-huh. And what was the horizontal asymptote of every single one of these?
0. Y 0.
Y equals 0. Yep. So then what was the difference between them?
They're just
They're
like
mirrored
inverted.
over the x-axis. One's negative, other's positive, I think.
Yep. They were basically flipped over the which axis?
Or
The
y.
Y.
The y-axis. Yep. So you basically had one that, if this was your x and y-axis, one went like this, the other one went like this, roughly. Right?
Do they have the same range?
So they still had the same range, yep. Same domain. The only difference was they were like mirror images of each other. Good stuff. And the last one. Then I had you graph these. Okay? 2 to the x, 3 times 2 to the x, 1/2 times 2 to the x. They were all members of this particular type of family when there's a number in front. What effect does having a value that's bigger than 1 or bigger than 0, positive, have on your graph?
The slope becomes more vertical as it crosses.
Yeah, like,
So it's like steeper?
Mm-hmm.
I put, it's on the right side of the y-axis, and the other one's on the left side.
Okay.
It's like going up.
So let's see. So we have steepness. All of these were they went up on the right side of the y-axis. Is that what you said?
Yes.
So I'm just going to draw a picture to model that. Anything else? Anything else we know? How about this? Everyone graph 2 to the x, 3 times 2 to the x, and 1/2 times 2 to the x. Everybody graph those in y1, y2, and y3. There's the 3 to the x, or the 3 times 2 to the x.
It's hard to tell anything on this one. It's like really small.
You can zoom in if you need to. Change the back part a little bit. Looking here, what do you see?
It's like they're all on the same line until they start curving. They have different y-intercepts.
They do have different y-intercepts. They do.
They're different. They don't have vertical asymptotes, does it?
Yeah. Exponential functions have no vertical asymptotes. What are the y-intercepts? What's the y-intercept for the blue one, the 2 to the x?
It's like 0.5. Is it going over the 1? The black one's 1.
The black one's 1. The red one is
1.5. Oh wait, no, the red one is
3. And the black one is 0.5. So this one was 1. This one was 3. And this one was 0.5.
Well, that makes sense because what's multiplied by.
For y-intercepts?
For their y-intercepts. Notice anything?
It determines where the
Y-intercept
It determines where the y-intercept is. The number in front. There's basically like an imaginary 1 times 2 to the x, is it not?
Mm-hmm.
A 3. A 1/2. 0.5. Okay. What about when k is less than 0? The y-intercept is lower. Like how low?
How low?
How low can you go? No, like how low is it? So how are these curving?
These are curving up. If you put it like I did negative 3 times 2x,
Mm-hmm.
and it makes the curve go down instead of up.
Oh yeah, inverse it.
So inverse it. So these are basically reflections over the
X.
So these are flipped over the X this time. Flipped X-axis. What about their y-intercepts? Real quick. One of them was a -3, right? If I press second delete, I can insert in a negative without having to retype everything. Yeah? Everybody knew about that one, right? And then -1/2. Insert in a negative. I know there's a -1 too, but I should have changed that one. Sorry. Ignore the blue one for right now. Here comes the negative part. -3. Looks like the y-intercept is
-3.
and then here comes the -1/2. Y-intercept's going to be -1/2, -0.5. Okay? So it looks like this is kind of like something to kind of keep in mind about your intercepts, right? Okay? What's the horizontal asymptote for all these graphs that we've seen so far? Y = 0. Because what changes our horizontal asymptote?
C.
C. What is C in every single one of these problems? 0. Okay? So that was kind of get you thinking a little bit, okay? Because you can draw some generalities about these different types of graphs, okay? The one thing I didn't have you guys look at was, I'm going to clear off the other ones, was when you had a number in front and a different, like an asymptote as well. I changed it. If I graph this, let's take a look. This is 3 times 2 to the x plus 2, right?
Mm-hmm.
Yeah, plus 2. What's going to be our horizontal asymptote? Y equals 2. Okay. What is our y-intercept?
5.
It's 5. How can we get that? If I have y equals 3 times 2 to the x plus 2, how can I get that without having to graph it?
You add
3 plus 2. If I add these, I'll be able to get my y-intercept every time. And then my C is still my horizontal asymptote every time. So we can take this investigation and we can take all these ideas, these in general ideas, and apply them to exponential models. Let's go to our notebooks. On page 38, this is the only thing that we're writing in on page 38, so kind of line up your foldable with where you want to put it so you know you're not writing it anywhere where you're not going to be able to see this. But this is the only thing we're writing on the actual pages of your notebook. And this is our general equation for an exponential function. Y equals A times B to the X plus C. And again, this is like the general equations, general equations for exponential functions.
Are we going to be writing to each one of those starting points?
So what was the domain of our exponential functions?
-infinity.
Yep. -infinity to positive infinity. It didn't matter whether we flipped it over the x-axis or the y-axis or who moved it up or down, the domain was still -infinity to infinity. Okay? However, the range kind of did change based off of what? The C, right? Now, up until I had you guys flip it over the x-axis on the very end, every single one of them went like this. Okay? And that lowest value, where it curved down, that was approaching your horizontal asymptote. So the domain would be, not the domain, the range would be what to what?
Your asymptote to
Yep, your asymptote, which is represented by what letter?
C.
C, to infinity. Now, do we include the horizontal asymptote? No, because it always got super close to it, but it never crossed or touched. And then, of course, we never include infinity. Now, yes, again, your range is going to change if you flip it over your x-axis. Then it'll be negative infinity to C if you flip it. But we're just talking about the ones in general without any flips or anything like that. What about the y-intercept?
0C.
What if there's an A?
Oh, then you have to add it.
When you add them. So it would be 0A plus C. That was bad. So whatever A was, we add to C, and then that's going to be our y-intercept. Our horizontal asymptote is always going to be your C, and it's always in the form of an equation. Uh-huh. And we talked about this very slightly. When B is greater than 1, when the base is greater than 1, say like 2, 3, 10, 1.3. What is it? What? I'm not trying to give it away. What do you notice about those types of graphs? Think about the very first 4 that we did. 2, 3, 10, 1.3. True. But they all did what?
They're positive.
What do you mean positive? Elaborate.
They're all going up.
They all went up to the right, didn't they? Every single one of them. But the second that we threw in a 1/2 in there, what did the 1/2 look like? When you,
The same, didn't it? It just was
everyone graph 1/2 to the x. Everyone graph 1/2 to the x.
Oh, it went the other way.
It went the other way, didn't it? It goes the other way. Same thing if I were to graph 3/4 to the x. That's still less than 1. It too will go down on the right hand side. So when b is greater than 1, the graphs are going to go up, but when it's in between 0 and 1, it's going to go down, aka exponential growth. And what's the other word? Who remembers? Decay. It's the difference between those two. And those are some of our general features for exponential models. All right, and the way that the foldables are set up, we're going to be working backwards. We're going to start with example 5 because I needed like the most space for the first example. So basically everything is backwards. So we're going example 5, example 4, so on and so forth. So applications. Many real-life situations involve growth and decay. Okay, growth, remember that's when the numbers are bigger than 1. Decay is when they're in between 0 and 1. Such as this first example that's located on it. It says example 1, but it's really example 5. Yeah. Talking about the length L centimeters of a pumpkin plant increases according to an equation. Now, if you're ever given an equation, then that's really good because pretty much you just have to kind of work with it. Where T is the number, or T is the time in days. And L, again, represents what? The length of the pumpkin plant. So we have this equation, and I asked you to complete the table. How do you do that? Plug in what? Plug in the values for T into the equation that you were given, okay? So I want you guys to do that. And if you look, it says give your answers correct to 3 significant figures, okay? So go ahead and do that. I'll give you a few minutes to get those values and complete your table. T is 2. What's the length?
5.76.
4.
8.29.
6.
11.5.
8, 10.
24.8.
Is it 8?
Yes. I just spoke wrong.
12,
35.7.
14, 16,
17.0.
74.0, and 18.
106.
Awesome. Okay. So then you have to graph this of L against T for T between 0 and 20 and L between 0 and 100. Now, if they, again, I mentioned this before, but they give you the restrictions, then that is how far you need to graph. There's no need to graph before 0 or after 20 in this particular graph, or bigger than 100 for your L. Okay? And a lot of times, that is how they give you the grade when it comes to the graph. Okay, follow and because you had to follow the restrictions they give you. What is going to go on a horizontal axis? Is it going to be L or is it going to be T? It is T. Your horizontal axis is always your independent axis. It's the one that's going to happen regardless of anything else. And time is always going to happen. Okay? L is what? It's going to be your length. Okay? Now, this right here is a variation of your centimeter paper. The only difference is that instead of 4 lines in between every thick line, it's supposed to be 5. So, but I'm trying to get you guys in the habit of recognizing that, hey, the thicker lines represent 1 centimeter. And so you want to make sure that if you ever have to create yourself, you go based off of the scale that they give you, okay? You have to go from 0 to 20. Clearly, 0 is going to start over here. And then every thick line, how do you think you should go? By 2s. That's good. And then on your we got to make sure it fits. We got to go all the way up to 100. So how can we go?
You can't do every individual. 75, 50, 25.
That'd be good. Okay? And then you're going to plot your points. I'm going to leave that to you guys, okay? Plot your points. We're going from 0 to 20. So that means it didn't ask us for 0 times 0, and it didn't ask us for time 20, but we might need those to graph, okay? Maybe. All right, so let's make sure that we do that. And I'm going to pause this. What was the value when t was 0? Well, it wasn't 1. If I plug in 0 into that equation of 4 times 1.2 to the 0 power, it's going to be what? It's going to be 4. Because think about it. Anything to the 0 power is 1. So that 1.2 to the 0 power is 1. So that's 4 times 1, which is 4. And then we're just going to do our best to draw a smooth curve through all the points. Now at this point, we're off the graph. We're out of the 100. But, it's pretty much kind of as far as we're able to go. Okay? So, there's your curve. Simple enough. All you got to do is just plot the points. And like I said, a lot of times they'll tell you how to graph this, to what scale. So in that way, like the points need to be on point. Here we're guesstimated because they're not like specifically, individualized and everything like that. But you do want to be specific on the ones that they do actually plot the points. They do take off if you don't plot them correctly. All right? How long is the pumpkin plant again when t equals 0? It was 4 centimeters. And again, we can get that by just plugging in 0 for t. And what about how long will the pumpkin plant be after 3 weeks? How do we figure that out? You plug in 21 for t. And why 21 and not 3? 3 weeks is 21 days. And t was in terms of days. So then we plug that in, figure that out, and how long will the pumpkin plant be? And don't forget your units. And there we go. Questions on this? Pretty straightforward, especially when you have the equation. Let's go to this example. Talking about Hubert. He invests 300 euros in the bank at a rate of 5% per annum compounded yearly. Oh, sound familiar? Let Y be the amount he had in the bank after X years. I said it sounds familiar because it should. Where have we dealt with this before? Interest. First unit, first test of this year. This one doesn't have an equation. You just got to create it yourself. Who remembers compound interest, that formula?
Like, present value.
That was in there.
Times 1 plus K, R over K 100. Exponent K. R. No, not R.
What was here on the other side?
Future value.
Future value. Okay? So future value represents how much money you had in the bank after a certain number of years. What are we going to use to represent future value based off of this problem?
Why?
Why? What's our present value?
3,000.
What's our rate? Yeah. What's your R?
R 5.
And what's the value of K?
1.
1. Because remember, K represented the number of compounding periods per year. And since it's being compounded yearly, that is 1. And then K is at the top. What are we going to plug in for N? X. So we're almost there with our equation. We're almost there with our equation. What's 5 over 100?
0.05.
0.05. So when I add it to 1, it becomes 1.05, and 1 times x is x. And there's your equation. There's your exponential function for you to be able to graph it using a scale of 0 to 10 years on your x-axis and 2,500 to 5,000 euros on your y-axis. Okay? You guys go ahead and graph this function on that grid that's given to you on your paper. Almost look like a straight line, but it is a curve. A little bit. Okay? And like I said before, you just want to make sure that you get the best scale possible for the graph that they give you. Okay? How much does he have after 4 years?
3650 euros.
Now we're talking about money. So how should we round?
Oh, so 3, 6, 4, 7.
2 decimal places. So when we type that in, it is 3. I don't remember the rest.
It was 3, 4, or 3646. 0.51875.
So 0.52 euros. So we are talking about money here. Anytime we're talking about money, there's 2 decimal places, unless it tells us otherwise. And then what about how many years is it before Hubert has 4,000 euros in the bank?
6. I got 54.
Hmm?
I got 54. 4,000?
Mm-hmm.
Wait.
To figure this one out, we're going to plug that in for Y, and we're looking for T. Now, the only thing about this, I don't know if some of you guys are using the table feature of your calculator. The only issue with that is that if T is not a whole number, that's the only time that the table really needs to be used. Okay? So in this type of case, Y1, Y2, see where they intersect. Okay? Because especially in this type of problem where it doesn't say like how many complete years it took Hubert to, get that much in the bank or anything like that, you want to get that decimal number. Okay? So we got to go into our y equals, type in 4,000, type in the function, And then before we click graph, what do you think I'm going to have to do? Change my window. Mine's all types of messed up because I've been using it for other classes. But my X-Men should be what?
2000.
Well, we're talking about time, right?
Maybe 10.
No.
Can't really have negative time, can we?
No, 0.
0.
Oh, X.
Our X maximum is going to change that back to 10. Ones. What about my Y min?
2500.
2500. And my Y max?
5000.
5000. Remember, you do have a graph too that you just did. Okay.
Oh, yeah.
What does y'all's change of X say? So I can just fix this back.
That. It says that.
It says this. Okay. So now when I graph it, there's the 4000 line. There's my exponential curve, and I'm looking for what?
Intersection.
How do I get there?
Second trace 5.
And then what I do after I go to second trace? That's not my answer.
You go over until you get like right over where it intersects, and
Then you press enter 3 times. So it's 5 point.
9. 0.
Mm-hmm.
But for years, when that should be 6 years, you can be like that.
You can leave it like this because, again, you don't know if the grader wants this one or if he wants the full year. So it's better off to put both because, again, it doesn't ask for the complete years. It just says the years. You can have fractions of a year.
Yeah.
So it's always good to include both of them. Again, the table is only used or useful when it's a whole number. And in this particular case, we do not know if it's asking for complete years or just years in general. So it's good to include both numbers.
Why are you talking to me?
Why are you talking to the screen?
Because she's recording
Here.
this.
All right. So from here, 3, 4, 3, 2, and 1. I want you guys to start with 3. And I want you guys to try these on your own, okay? So I'm going to give you about 3 minutes, and I'm going to check in to see how you did. If you finish up example 3 and 3 minutes isn't up, go on to example 2, okay? All right. So we have an equation, 150 times 2 to the t, where n is the number of bacteria present and t is the number of hours since the experiment began. So it's asked you for the number of bacteria present at the start of the experiment. That basically means when t equals what? 0. So 150 times 2 to the 0 power is going to equal what?
150.
150 bacteria, exactly. And then it asked you how many you had after 3 hours. That's basically when t equals 3. So you're plugging in 3 for t, and you get how many?
1200.
Simple enough, right? But then this one asks you, how long does it take for you to reach 19,200 bacteria? So this time, you're looking for t. So what are we going to do?
Plug it in Y1 and
Y1 and Y2, we can definitely look at the intersection point, or this one actually was on our table, was it not?
Yes.
It was. And what's the value of t?
7.
It took 7 hours for the bacteria to reach that much. Good stuff. I see some of you guys are already working on example 2, right? Okay, I'll give you another 3 minutes and then I'll check in. And if you finish example 2, go to example 1. Let's go over this one. Don't overthink these, okay? Especially if you're given points that are on your exponential. Just like how when you were given points on your quadratic, didn't we plug in an x value and a y value or something to try to figure out something that's missing? You can do the same thing here. You know that x is 0 and a is y. So you can actually just set up an equation and plug in 0 for x, plug in a for y, and solve that way. What's 3 to the 0 power?
1.
What's 1 plus 2? So a is 3. And then you can do the same thing to find b. Plug in b for y 1 for x, and solve for b. When you do 3 raised to the negative 1 and then add 2, it's not a whole number. It is a decimal / a fraction. I prefer the fraction answer, but you can give me the decimal and 3 significant figures.
I have 2. I thought you said B could
7
be
over
below 2.
It cannot be below 2, which is not. It's 7 over 3, right?
Right.
Which is 2.33.
Oh.
So it's very close to it, but it's not at 2 yet. And our equation for our asymptote is y equals 2, the value of c. Okay? Yes?
Can you just put like 2 for B with that?
No, because it got the decimal points after it, so you got to put the decimals. Yes?
I'm so confused with like the asymptote thing. Like I don't understand how you find y equals 2.
Okay, so remember from our investigation, like what we did earlier, whenever it's in this format, okay, where you have some base raised to an exponent plus another number, this number is your asymptote every single time. So because we have that plus 2 there, that 2 is going to be where our asymptote is in this curve. And if you're still unsure, you do have the equation, so you can go to graph it. Yeah, it's your asymptote, not your y-intercept.
Okay, that's why I thought it was 4 because I thought that one was 2.
Mm-mm.
I thought A was 2.
No, your A was 3. And so once you graph it, think about it, you can always press trace, and then you can just kind of follow along the curve and look at the y values. As x is getting bigger, y is getting closer and closer and closer to what number? And as you see, the further you go, y is getting closer and closer and closer to 2. All right. And now this last one we'll do together so you guys can have some time to get started on your homework in class. Now, I know we've talked about the value of C is the horizontal asymptote. Yes, you can look at this and you can see that the horizontal asymptote for this graph is going to be what? Negative 10. So yes, C is negative 10. And you could probably do some other ways to decipher to find the value of K. But the way I'm going to show you how to do this problem, it might be helpful for future problems, okay? Because they might not be this easy, all right? You see how we have a point on this curve? 2 points, actually. What's this point right here?
0, negative 5.
And this point?
0, 0, 5. I mean 0, 1. Oh, 0, 1.
1, 0. Let's make sure we get them right. What we can do is we can take both of those points and plug them in to our equation. Plug in 0 for y and 1 for x. What's 2 to the first power?
2.
So this is basically 0 equals 2k plus c. We can do a similar process with this point. Plug in negative 5 for y and 0 for k. What's 2 to the 0 power? 1. So we have negative 5 equals k plus c. And now we have 2 equations with 2 variables.
So you just find like C or K and then plug it into the other equation.
Mm-hmm.
You plug in C.
Substitution, or you could do, what's the other one?
Elimination.
Elimination. But you can do it, and this works every single time. Because even though, yes, again, I know this is an easy problem, and you can just look at it and see where your horizontal asymptote is, and maybe figure out how to find K as well, but they won't always be this straightforward and easy, okay? So I'm trying to give you the skills that you can use for future problems on the ones that are not as easy, okay? So what variable do you want to eliminate?
C.
C. How am I going to eliminate it? Negatize everything, yes. These go away. What's 0 plus 5?
5.
And what's 2k minus k?
K.
So 5 is k. Boom. Just like that. Then I can take that value and plug in. -5 equals 5 plus c. How do I solve for c? Subtract 5. What's -5 minus 5?
0. Wait. Never mind.
-5 minus 5 is
Yep.
0, right?
And then there you go. Now again, I know you can just look at it and see some of this stuff. And yes, if it is that straightforward, then yes. But if it's not, this skill is going to be so helpful. Okay? This skill of plugging in and solving like a system, because this is the mathematical models unit, will definitely be helpful. But using all those properties, all the general features about domain and how to find y-intercepts and asymptotes and all those things, those are going to be helpful for you. And I hope that investigation really did kind of open your eyes to some things about exponential functions. And then these examples just added on to that. All right?